1, 0.
1, 2, 3, 4.
Hi everyone, here's our final lesson for polynomials, and we're going to look at some word problems, some applications today. So there's a few different types of word problems that emerge, and the first one we're going to look at is a box question. There's actually two box examples that we'll take a look at today. So a box is constructed such that the length is twice the width and the height is 2 centimeters longer than the width. And in total, the volume is 350 centimeters cubed. Find the dimensions of the box. So this question can be done several ways. It can be done algebraically, and it can also be done graphically. And so the big thing, you'd have to ask your teacher, but what we're going to do is we're going to find out the fastest, most efficient way to be able to do this. And that's going to be looking at it using our graphing calculator. But we're also going to try and make sure that we can show how to do it algebraically in case you're asked to do that as well. So if the length is twice the width, what if we call the width x centimeters, and then the length is going to be twice that, so we could call the length 2x, and the height is 2 centimeters longer than the width. So if the width was x, we could say the height will be x plus 2. So there's our dimensions, and we know that for volume of a box we have length times width times height. So we could say, we could now fill in the length and the width and the height, and we know that's all going to equal 350 centimeters cubed. So instead of saying volume, we can replace it with the 350 that it is, and then you could say that's going to be equal to 2x times by x plus 2. So based off of that, you want to figure out, well, what's the best and fastest way to be able to answer something like this. And what I'm going to recommend is that you take your graphic calculator and you put 350 in for y1, and then you enter in the second part here, the 2x times the x plus 2 in for y2, and we see if we can find a solution for this just graphically. And so let's do that right now. So if we take a look at our graphic calculator, you go to y equals, and you have 350, and then for y2 we had an x, we had a 2x, sorry, 2x times x plus 2. And you want to graph this. Now before we graph it, and we got to get more comfortable in terms of being able to estimate what a proper window is, you want to go to your window and you want to think about what's realistic here. And for the dimensions x, that's representing the dimensions for the sides of the boxes. And so you're not going to have a negative dimension. So we can make our x min 0. Let's keep our x max 10 for now. And in terms of y is representing the height or the volume of the box, and we know that it has a volume of 350. And so let's make our y min 0, and so that we can see everything happening from there and above, let's make it 500. If you graph that, you're going to get some part of a cubic function, that's the red graph right there, and it's going to intersect with the line of y equals 350. And what we want to do is we want to find its solution. We want to find the x value of where they intersect right there. So if you press second trace intersect and you go enter, 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 you'll find out that it intersects exactly when x is equal to 5. And when you go back to what we have right here, we could do a quick test, and you could say, well, what would happen if x equaled 5? Well, you would have a length of 2 times 5, a length of 10 centimeters. You'd have a width of 5 centimeters, and you'd have a height of 5 plus 2, which is 7 centimeters. And if you do 5 times 7 is 35, and 35 times 10 is 350, then that quickly confirms that yes, your answer is when x is 5, that would satisfy those dimensions, and the dimensions would be 10 centimeters by 5 centimeters by 7 centimeters. And that's a really quick way of being able to solve this. It's important that we also take a look at how you might solve this algebraically, and that part isn't quite as quick. So I'll do my best job to try and be able to explain that as well. So you could say 350 is going to be equal to, and let's try to clean up the right side here. And then from here, what you could do, oh, sorry, I made a little mistake here. This is going to be 4x cubed, whoops, 2x cubed plus 4x squared. And there we go. So then based off of that, what we want to do is, you'd say if I was to solve for this, based off of what I learned in 3.4, is I should make one side equal to 0. I could have 2x cubed plus 4x squared plus 0x minus 350. And we want to be able to factor and solve that. And so then you would look at the rational root theorem and you want to say, well, what are some values that could possibly work for something like this? And of course, you would have to look back to this constant. You could actually say, well, I could actually simplify this a little bit. And before I even look at the rational root theorem, I could factor out the greatest common factor, which is 2. And I could say 0 equals 2 bracket x cubed plus 2x squared minus 175. And you'd have to list all of the factors for 175. And if you start listing that out, you would say, okay, there would be 5, 25, oh no, sorry, 7 actually goes into it as well. 25, 35, and 175. And you'd have to say, well, of these rational root options, I need to test and see if any of those would potentially work for what we have right there. Now, because we've already done this by using our graphing calculator, we know that x equals 5, 5 works. So let's try 5 as a factor. And we're going to try it as a factor for this x cubed plus 2x squared minus 175. So if you take 5 and you say 1, 2, 0x's minus 175, you would be left with something that would give us a remainder of 0. And then you'd be left with x squared plus 7x plus 35 equals 0. So you may actually have 2 additional answers. We know that x equals 5 works, but is there another way that could also work? And you would try to factor the x squared plus 7x plus 35, and you would find that I can't think of 2 numbers that times to 35 and add to 7. And if you can't do that, that doesn't mean that it can't be factored. It just means that there's probably not going to be a rational root, but there might be an irrational solution. And if you wanted to be able to test out what additional options could work for that, you have to throw it into the quad. And so you could use your negative b plus or minus the square root of b squared minus 4ac all over 2a to be able to see if potentially there might be more answers than just x equals 5. And so when you enter that into the quad, you would get negative 7 plus or minus the square root of 7 squared minus 4 times 1 times 35 all over 2 times 1. And quickly, when you put this in, you would find that your radicand, the part underneath the square root right here, is negative, and it would produce no solution. There's no additional solutions that would come from that because you would have a negative root. And so based off of that, your only solution is 5. And based off of that, you could say my dimensions are 5 centimeters by 7 centimeters by 10 centimeters. So just to be really clear for my class, we want to see that you're able to solve this using your graphing calculator. You'd have to be able to come up with a proper equation, and you'd have to be able to find out what your dimensions are based off of that. The algebra here, treat this as a bonus to show that, hey, we're able to do this based off of everything that we know, but I'm not going to be asking for that on an assessment for what you have right here. Okay, let's look at a second example. An open rectangular box is constructed by cutting out a square length of x from each corner of a 28 centimeter by 19 centimeter piece of cardboard and then folding up the sides. So we have a cut happening in each of these four corners, and they're all going to be represented by length x. They're equivalent to each other. And then you're going to bend up the dimensions of the box. So you create this open top box where each of these corners are cut out, and you can fold up the sides to make a box. So based off of that, the question is saying, write the volume of the box as a function of the side length x of each square cut. So we have a length, and we have a width, and we have a height. And we want to come up with some dimensions for what could potentially happen with this. So if the length of the box is originally 28 centimeters, and if you go back to the diagram here, if you're placing something in which there's a cut of x here and a cut of x here, then the new length of the box, once you fold up the sides, is going to be the full 28 take away 2 x's. Just like the full width of the box is going to be the full 19 take away 2 x's. So the dimensions of your box would be a length of 28 subtract 2x and a width of 19 minus 2x. And then the height of the box is going to be x. That's the cut that you made that you ended up folding upwards. And so if you wanted to put that all together and write the volume of the box, you could say volume equals x times 28 minus 2x times 19 minus 2x. Now I wrote the height first just because having the x in front is probably the most proper way of being able to express that, but that's something that we can use to represent a general function for this particular box. So part B is now saying, it's asking us to graph it, and it's saying what's the maximum volume that you could possibly create. So it's actually a very interesting question. If you have a piece of cardboard, what would be the ideal size to be able to make a cut into the corners so that you can maximize the dimensions of the box, so you can maximize the volume of the box that you have. And so given something like this, we're going to want to be able to graph it, and we know that when we graph it, we're going to create a cubic function, and whatever that cubic function looks like, it's going to have at some point a relative maximum, and we want to be able to find out what's happening at that relative maximum so we can identify what would be the dimensions to be able to maximize the volume of the box. And so if you go back to your graphing calculator, and let's go here and let's clear this, and let's go up to something in which we could now say, okay, we had x 28 minus 2x and 19 minus 2x. So if you have something like that, and you want to think about what a reasonable window would be, we could go back to window, and we know that x is representing the length of the cut of the box. It's also representing the height. So we know we're not going to have a negative dimension, so we can make it 0. And you could make the x max 10. That seems something reasonable. There's a lot of talking points around this. If you go back to something like what you look at here, you know that x could actually never be something bigger than 9.5, because if it was bigger than 9.5, then this part here would be a negative value. So you could say that, but for the sake of us, we'll actually leave x at 10, just in terms of what we're looking at. And for the volume, we don't know what the volume is. So saying 500 could be something that would be a reasonable maximum volume. You could really figure out a bunch of different things. It's something you probably have to try several times. Let's put in 1,000. Let's see what happens when we have that. But knowing that if we'd put in 500, we just might not see our relative maximum. So we can graph that, and you get something that looks like part of a cubic function. Now, we don't have the entire cubic function, and we don't have the entire cubic function because we limited what our x max was. If we showed our x max to be something a little bit more like 20, you're going to get a little bit more shape of what the full cubic function looks like. But we know that we're not going to have to worry about that much of it because we know that our x max can't be more than 9.5, because if we had something like that, we would have a negative dimension. So we go back to our graph here, and we know that in this particular case, we're only really concerned about finding the relative maximum, this point right up here. So to find a maximum, we'll go second trace max, and then we know we have to be left bound and then right bound. So go to the left of it, press enter, go to the right of it, press enter, and then we can trap it one more time, and we're going to get something in which we say the x value will be something like 3.7. It didn't say what to round it to, so we'll just say 3.7, and then the maximum volumes can be, we'll say 884 centimeters cubed. And so based off of that, this is telling us the height when our x value is 3.7, we produce the maximum possible volume of the box, and the maximum possible volume of the box is 884 centimeters cubed. So going back, that's not good. Okay, going back to the question right here, when it says graph it and then explain what are the dimensions when the box is this maximum value. Well, we can start to do that because we could say, well, it roughly looked something like this based off of the window that we had right here, and we knew that this produced something where we had, it doesn't say what to round it to, so we said 3.7, and then we said 884, we'll say 884.2. Okay, and if they're asking for what is the maximum volume of the box, that's going to be 884.2 centimeters cubed. And then if they want the dimensions that would produce that, and you have your length and your width and your height, then what we could do is we can take that 3.7 and we could sub it in here and here and here to be able to figure this out. So our height is going to be 3.7 centimeters, and then if we do 28 minus 2 times 3.7, we get 7.4, so we get 20.6. And then for our width, we would get something that would be 9 less than that, so we would get, I think that would be 11.6 centimeters. And so you could test this, and if you did 20.6 times 11.6 times 3.7, let's just confirm what we get when we do something like that. So 20.6 times 11.6 times 3.7. And sure enough, when we do something like that, we get 884.152, and that's almost bang on with everything that we had. It might be slightly off from your exact value, but that's a pretty reasonable estimate in terms of what we're looking for that. So I feel pretty good about how we answered that part. And then part C is saying, well, what size of square should be cut from the corners if we now don't want the maximum volume? We don't care about the 884, but we want something that's going to produce a volume of 750 centimeters cubed. So you could go back to your graphing calculator, and then based off of this, you could go back to y equals, go to y2, and you want to put in 750. And when you do something like that, and you graph this, you can now see, you can now see that there's going to be something here where there's an intersect here and there's an intersect here. And that's when you produce a volume with a height of 750. That red line is representing 750. So if you go second trace intersect and you want to be able to trap that, you can go nearby there. And let's do this. We'll do this to one decimal place again. And you're going to get something here that's going to say, well, we'll say 2.2. And then to find the second one, second trace intersect. Okay, and we get 5.5. Okay, so those are two intersects from that. And so if we want to figure out what our solutions would be from here, then it means that there are two possible ways that we could potentially build a box that would have a volume of 750 centimeters cubed. So you can do it once when you had a cut of 2.2 centimeters, but you could also do it when you have a cut of 5.5 centimeters. In other words, you could have a box that's a little more flat, or you could have a box that's a little more vertical. And you want to be able to list both of those solutions. And so what we can say here is you can say here's box 1 at 2.2 and here's box 2 at 5.5. And you could say what would happen to the length and the width and the height, and the length and the width and the height. So we know that for our height here, it's going to be 2.2. This is going to be 5.5. And then to find out the next part here, you know you had 28. Let's go back to our calculator. Whoops. Okay, and let's go 28 minus 2 bracket, and then we said it was 2.2, so we can type in 2.2. And you get 23.6. So if we have something that's going to be 23.6, then we can figure out the rest of our dimensions here. So we could say that's 23.6, that's going to be 9 less, that's going to be 14.6. And that's one set of our solutions. And then if you do the same thing for the next one here, if you did 5.5 and that gets doubled, then you'd have 28 minus 11, so you get 17. And then minus 9, you get 8 centimeters. And if you did something like that, you could check your answers again by timesing the length and the width and the height by each other, and hopefully you would get something that would check out. So what I mean by that is if I did 17 times 8 times 5.5, I should get something that's going to be very close to 750. So if you check something like that here, you could say, okay, well, what would happen if I had something like that? And I wanted to do, I want to check out those dimensions. So I could say 17 times 8 times 5.5. And you get an answer of 748. So you don't get an answer of 750, and that's because that 5.5 was a rounded answer, but it's going to be close enough to something where you could say, I feel pretty confident that I did this correct because that's pretty close to 750 based off of the rounding that we were allowed to do for that question. Okay, so we have one more example to take a look at right here. This question is going to talk about a cylinder, but it's also going to talk about a hemisphere. And so one thing I should add on here is there's this doesn't give an example of doing a silo question, which is a pretty common example for these sorts of word problems. So you might want to take a look at making sure you know how to do some of those silo questions as well. But there's a couple formulas that you need to know here. So the first thing is for volume of a cylinder, you know you have volume equals pi r squared h, so area of the base times by the height. And then you're also going to have to know something about the volume of a sphere. And so volume of a sphere is going to equal 4 pi r cubed divided by 3. So think about each of those when you set this up here. And again, we'll try and solve this using your graphing calculator as the most efficient way. So if you're to draw a vitamin capsule, get something that looks like this. And it has the shape of a right circular cylinder with hemispheres on each end. And so we can cap it right here and here. And it says the total length of the capsule is 14 millimeters. So from end to end here, this is going to be 14 millimeters. And its volume total will be 108 millimeter or pi millimeters cubed. And it says find x, the radius of the capsule. So right here, from here to here, this is going to represent x, just like from here to here, that would represent x. Okay, so this question has two hemispheres, and if it has two hemispheres and you put those together, that would equal the entire sphere. So we can use that full part of the formula right there. And if it was just one of them, then you'd have to half your formula, and it would be 2 pi r cubed divided by 3. If we wanted to take a look at something in terms of what we have, we could say volume is going to equal, in this case, the volume of the cylinder plus the two hemispheres put together. And we know that this is going to equal 108 pi, which is going to equal, well, let's see if we could start to figure some stuff out here. So in terms of the cylinder, we could say that would be pi, and it's saying the radius is x. So let's say pi x squared, and then what would you say is the height of the cylinder? Well, the height of the cylinder is going from here to here. And if the entire length of the capsule is 14 and you're subtracting the two x's, then the height is going to be 14 take away 2x. And we can use x cubed for the radius there again. And now we have something in which we have enough information where we could put this into the graphing calculator and we could find out our solution pretty quickly. So once again, let's give this a try and let's see what we could do here. Let's put this in for y1 and let's put this in for y2. And then let's see what we could potentially get from that to just be able to say, can we find out our solution the fastest way possible? So we have back here in our y equals, let's clear this. Okay, so our y1, we said we had 108 pi. And then our y2, we had pi x squared, and then here we had 14 minus 2x. That was the area, that was the volume of our cylinder, and then we're going to add that to the spheres. And for the spheres, we had, let's just take a look at this again quickly, we had 4 pi x cubed over 3. So we'll say bracket 4 pi x cubed, whoops, close bracket, divided by 3. Okay, here we go. Okay, now do we need to change our window? I think we do need to change our window. If we take a look at this, x is representing the length of the capsule, and we can leave it at 0 to 10, but it's probably not going to be something close to 10, it'll be something significantly less than that. And we know that our volume is 108 pi. 108 pi is a little over 300, so let's make our max volume 500, and then let's graph that. And sure enough, we get an intersect quite quickly. So we can go second trace intersect. We can go near to where it intersects, and we want to press enter 3 times. And we get a solution of x equaling 3. And so if x equals 3, then we can go back here and we have our answer right away. X equals 3. And so the radius of the capsule to produce something like this is going to be 3 centimeters. Now, once again, let's see if we could show some of the algebra here, and let's see what would happen if we did some of this algebra. Okay, flash forward, take a look at what we have with the equation here. What we've done is we've taken our denominator of 3 and we've times it to each of the numerators. So we've times it by 3 here and here and here, sorry, and there. And we've also said each of the individual terms have a pi, so we could factor out or reduce everything by a pi. And what we'd be left with if we did something like that is we would have 3 times 108, which would be 324. Whoops, sorry. 324. And it'd be equal to, over here, we would say we'd have a 3x squared times 14 minus 2x plus 4x cubed. Okay, and so now what we could say is we can expand this in here. And we should get everything onto one side. So you could join these like terms and you get negative 2x squared. Let's bring that all onto the left side and we get positive 2x squared minus 42, sorry, positive 2x cubed minus 42x squared plus 324, oh my goodness, equals 0. From here we can factor it to 2 and we'd have x cubed minus 21x squared plus 162, and we want to see what can we do with this. So we can look at that and we can say, well, our rational root theorem would look at factors of things that would multiply to 162. Okay, so if we wanted 162, we could say, well, there's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, dot, dot, dot. And you want to try and test a number that's going to be able to give you a remainder of 0. Now we know that the answer is 3 centimeters, so we can try plugging in 3, and let's see what would happen. If we plugged in 3, we get 27 minus 9 times 21. And sure enough, that does give us 0. So we know we're going to do a good job with that. And let's do our synthetic division and see what happens when we plug in a 3 here. So we had 1x cubed minus 21x squared plus 0x plus 162. That gives us a remainder of 0, and then we're left with something in which we would have factors of x squared minus 18x minus 54. And you'd say, what are two numbers that times to negative 4 and add to negative 18? And if you work that out, you're not going to get anything worthwhile. So we could put that in the quad again just to save some time. We're not even going to worry about that. And we're just going to say, hey, algebraically, we're able to show that yes, x equals 3. And that's our solution for our radius. So thanks for joining us, and hopefully you enjoyed the word applications part of that. There's some questions here to be able to work on, and we'll see you next class.